Sorry, I forgot to upload these to the other class. We'll get yours in a second. Alright, I'll upload theirs later. Nope, we're good. Okay. Um, Today we're going to start alcohols, and we're going to we're going to look at how to name them, how to make them, and then we'll go with what they can do. So let's take a look at the alcohol as a functional group. Alcohols form the general pattern of ROH, right? They have a hydroxy group. And we're going to see that they can come in multiple types. We can have a primary alcohol, a secondary alcohol, or a tertiary alcohol. So primary alcohol is on the end of a chain. Secondary alcohol is on a CH2. Well, now it's a CH. And then the tertiary alcohol has got 3 carbons bound to the alcohol containing carbon. So we call those, primary, secondary, tertiary. Just like we would call the carbons, the carbon that is on is primary, the carbon that is on is secondary or tertiary. So we have all of this lovely information for us. We're going to see that naming alcohols, we have, as always, well, I suppose not as always, we're going to see that sometimes we name them as prefixes. If they are a prefix, meaning you have a higher priority group, somewhere, which is not the case. For right now, alcohols will be our highest. That one, the name is hydroxy. So if you have something that's got a higher priority than an alcohol, so say you have a ketone or something, if you're naming that ketone, you'll name an alcohol as a hydroxy group upon your molecule. However, if they are the highest priority group, then we will change the name of, say, alkane to alkanol. So, for example, butane, butanol. Butane is this. Depending where we have it, we can say we have 2-butanol, which would indicate that we have the alcohol on the second carbon. And in this case, we would also need stereochemistry because that would be a chiral center. So priority 1, 2, 3. This is R 2-butanol. That we could have 1-butanol, not a chiral center, so we don't have to worry about that. If we want, we could also say butan 1-ol. That works. Or R butan 2-ol. Either of these are okay. Once we start putting more and more substituents on, the putting the locator number closer to the ol makes it a little bit easier. So you'll see these more and more once we have more and more substituents on there. With cycloalkane alcohols, cyclobutanol, we do not we don't need to worry about a locator number here because it's assumed that it's going to be on carbon 1, since this is a cyclic structure. With a linear structure, we do need to indicate the 1 if it's on the uh, the first carbon. You might see it as N-butanol, which means it's all linear, but normal butanol. But it's kind of still obligatory to put the 1 there. With cyclic ones, it's not necessary. So if you had something like this, those are both wedges in my lovely drawings. If we take a look, priority 1, 2, 3, this one is R. Was the other one S then? Did I totally mess that up? 1, 2, 3. No, that's R. Okay. Priority 1, priority 2, priority 3. This one is S down here. Don't forget all that stuff. We would say that this is SR 2 chlorocyclobutanol. I forgot my numbers. So 1S2R. We need to indicate that we have 2-chlorocyclobutanol, both of them on wedges. And of course, I can go crazy and give you something with all these carbons and all that. We'll not worry about that quite yet. With multiple alcohols, your longest chain must contain both of them. And in fact, we'll throw that in there too. With multiple alcohols, right now alcohols are higher priority than alkynes, alkenes, so they are our highest priority. So just like before, we're going to always put as many of them into our longest chain as possible. So try to put as many as you can here. So our longest chain has to contain both alcohols. So that's going to be our longest chain there. So that's 4 carbons. And so the parent name for this thing, Ben. Nope, let's try that again. We're going to have to say that this is carbon 1, 2, 3, 4. We always start numbering from the ones that will give us the lowest numbers. We heard someone outside. Okay. She's going to go kill them now or something. Okay, so we're always going to have our lowest numbers possible. So if we do it this way, we're going to get 1, 2, 3 as our locator numbers. If we did it the other way, we would get 2, 2, 4. So 1, 2, 3 is better. So this is going to be but 2 ene 1, 3 diol. That's our parent name for this. We have an alkene on carbon 2, carbons 2 and 3, but we always say the first one. And then on carbons 1 and 3, we have 2 alcohols, and so we would call it a diol. Like we had butadiene before for 2 alkenes, here we have diol for 2 alcohols. And in this case, we have some stereochemistry as well as that propyl group to deal with. So the propyl group 1, 2, 3, that's going to be on carbon 2. So we have 2 propyl, but, I guess we don't need the hyphen there, but 2 ene 1, 3 diol. And then we have our stereochemistry. So carbon 2, that's going to be an E alkene. Carbon 3 is 1, 2, 3, that's an R. We technically don't need to put the 2 there, but we'll do it for fun. And then, so our full name for this thing will be 2E3R 2 propyl butene 1,3 diol. Should be a hyphen there. So, naming these much the same as naming regular compounds. We just are adding in the OL suffix. So at the end of the molecule, our parent name is the alcohol. And, if we had 3 of them, it would be triol. If we had something like this, why did I put this on a wedge? Shame on me. That's not a chiral carbon at all. So we can just put E. Shame on me. Okay. Shame on all y'all. Perfect, Kevin. Thank you. Kevin already got it as I was saying it. Perfect. Yeah, I saw that. I think it's the same time you wrote it out. So cool. What was I saying? Let's do the same thing. Now we'll put a wedge on there. Okay. Now we're going to have to name this nonsense. So we have 3 alcohols, but there's not really a way to put all of them on there. Right? We don't have a way to make one chain that has all 3 alcohols. So we're going to want to include the longest chain that has the most of them. And so that's going to be this chain in the middle. That one is 6 carbons long, so we know that this will be a hexene. And say if they were equal, we're going to choose the one that has the alkene as well. We always want to put as many high priority things into our parent chain as possible. So if one side had 2 alcohols, yeah, exactly. Jackson's got it right. If one side had 2 alcohols and the other one had 2 alcohols and an alkene, you'll want to go with the one that gives you the most stuff, assuming they're the same length. In this case, that's what we're doing. We are going to choose the one that has the most alcohols and the most carbons, and so we're going to go from there. So our parent name here, we're going to start here, because that'll give us the lowest numbers. So we're going to have as our parent name hex 2 ene 2 4 diol. That will be our parent name for this. So we now have to then just put in our stereochemistry as well as our other group there. We have the hydroxymethyl on number 3. So we're going to see on, I guess we can just say that. So we're going to have to name that as a substituent within a substituent. With the extra E, butene diol. I'll double check that, Kevin. So we'll deal with that. With this hydroxymethyl, we're not going to need a locator group. If we, oh, you accidentally put one. Okay, got it. If we had another carbon in here, we would have to put a locator number. We'd say 1-hydroxyethyl. But since we don't, we do not need a locator number within our parentheses. 3-hydroxymethyl. And then we have on our 4th carbon there, we have a 1, 2, 3, we have an S. So 4S, 3-hydroxymethyl, hex, 2-ene, 2,4-diol. And so that would be the name for this thing. And yeah, so you're absolutely right. Jack said that you would need to put the substituent with the substituent, and in that case, you always use the prefix terminology, so it will be hydroxymethyl there. All right, cool. So that is naming alcohols. If we want to talk about how to make them, we've covered a lot of reactions, and we're going to learn a few more. How to make alcohols. And this is not, some sort of bathtub gin type of thing going on, right? We're talking about the functional group, not the substance. So making alcohols, we've learned a couple ways. We can do substitutions. If we take if we do an SN2 type of reaction, we can get an alcohol out. If we do an SN1, probably unlikely on this, but maybe do it on the secondary one. You can make alcohols by substitution. Of course, primary ones you do SN2 for tertiary, you do E or SN1, but with secondaries, you could presumably do either. Although again, it's less. Both of them, it's not favorable for either one. So we'll have that. So that's one way we can make alcohols that we know so far. We also know that we can go from alkenes to alcohols. So we can substitute onto an alkyl halide. We can also add two alkenes. We saw that if we give it acidic water, you can end up going through the carbocation mechanism, putting your OH on the Markovnikov side, but you'll form a carbocation. Don't forget that. We saw that we can do oxymercuration with water, and then demercuration with the sodium borohydride. Or we could do an anti-Markovnikov hydroxylation with BH3, THF, and then second NaOH and peroxide. So we have quite a few ways to make alcohols from alkenes, and that's just to make a single alcohol. We can make multiple alcohols too. So we can add things to alkenes. Awesome. You can do hydrolysis. You could do oxymercuration, demercuration, or you can do hydroboration oxidation. That'll give you a single alcohol. You can add multiple alcohols. You can use either basic or acidic conditions on an epoxide to give you antihydroxylation, even though I'm not going to I'm putting the wedge and dash on there just to remind you that it's anti, even though, yes, I understand the wedge one doesn't matter because it's not a chiral center. And of course, you'll have the enantiomer. But it's still an anti addition, right? So you'll oxidize to the epoxide and then use either base or hydroxide in water or acid in water, and you'll end up opening up that in to make the anti-dihydroxylated species. You can do a syn dihydroxylation using the osmium tetroxide and what did we use? Sodium sulfite. That would work. Remember, this is this is syn. So we have a few ways to do this. We can also do a cold basic KMNO4 that would also get us to the same product. So we can make diols as well from alkenes. All right, so lots of ways we've already talked about to make alcohols. These are ones we have learned already. So this is a review. There are a few ways that we haven't learned yet that we will learn, mainly through reduction of carbonyls, and we're going to talk about that in a sec. Do we have any questions on the ones that we've covered? So here, let me flip to the so we have substituting an alkyl halide. Of course, that's going to be on an sp3 carbon, right? You can't do that on sp2 carbons. You can add things to alkenes. We have 6 different ways to do it. 3 of those ways gives us a single alcohol. 3 of those ways give us diols. So we have lots of ways to do this. Lots and lots of ways. All right. So we have all these ways so far. Let's talk about new ways to make alcohols that we haven't looked at yet. All right, so if we're looking at new ways to make alcohols that we haven't looked at before, primarily we're looking at reduction of a carbonyl. And if we're going to talk about reduction, of course, the opposite of that is oxidation, right? Um, if we're going to talk about redox stuff, we're going to look at it in the lens of organic compounds. We use different sorts of ways of determining oxidation state with carbon than we do with the things like sodium sulfate or whatever. We have very different ways of talking about um, these sorts of things. So with kind of reduction and oxidation, of carbon, we can look at oxidation numbers, of course. We can say, yes, we are going to take a look at our carbon and look at the electrons and what's more electronegative than this or whatever. We can do that. We can also think about reduction and oxidation by having reduction being we're adding CH bonds to our molecule. An oxidation would be removing CH bonds. Or conversely, we are removing CO bonds, or adding, for oxidation, we're adding CO bonds. Typically, oxidation, we're talking about oxygen. Go figure. Although technically we can talk about nitrogen as well. We can oxidize things to nitriles. We're adding more CN bonds. So we can oxidize things to nitriles. Reduction means we're adding CH bonds. Oxidation means we're getting rid of CH bonds. And so we've looked at reduction before, right? We saw that we could put this with H2 and platinum, or some other catalyst, palladium, nickel, whatever. We would then get hydrogens on this, right? We have each carbon here has one hydrogen. The carbons of the alkenes have one hydrogen. When we reduce, we are adding more CH bonds to our molecule. So this is a reduction reaction. We know this because we're adding CH bonds. Adding CH bonds. Oxidation would be the opposite. If we are eliminating something, that is an oxidation. We are going to be removing CH bonds. That's like something like an elimination. We are removing CH bonds. This is a reduction. And again, while we do talk about these in terms of carbon to oxygen bonds, sometimes, technically speaking, these would be also covered by carbon nitrogen and carbon halogen bonds. Those would all fall into the same categories there, the opposite of hydrogen. If you want to look at it in terms of oxidation number, oops. If we want to look at oxidation numbers to determine if redox is happening or not, we have to figure out a way to do this. And when we're doing this, we're going to end up breaking our bonds. We are going to break CC bonds homolytically. I'm not going to be able to fit that. And we're going to break all others heterolytically. If we're looking at oxidation number. So, if we're breaking carbon-carbon bonds homolytically, that means we're going to be breaking all of these. Wow, those are so many arrows. I'm going to redraw that. We have now 3 dots. And then we have our CH3s. Who cares about those? Whatever. For breaking the rest of them heterolytically, we have to look at what's more electronegative. And in fact, carbon is more electronegative than hydrogen. So those electrons are all going to go to carbon. And as a result, we're going to have, in both cases, carbon that is negatively charged. They have 5 electrons, that's a minus charge on carbon. And so these will both have an oxidation number of -1. These are our oxidation numbers. And remember, if we're looking at redox, we're looking at what's happening to oxidation numbers. And so we can't, in Gen Chem, we could just say, oh yeah, we're going to add up all our things, make H plus 1, the C's will take the rest, and, to balance it out. But because each carbon is different here, 2 of them are different, we want to look at the oxidation numbers on each specific carbon. And the best way to do that is to break all the bonds and see what's been connected. All carbon-carbon bonds are homolytically broken, meaning you get 1 electron from that bond. All other bonds get heterolytically broken, which means the electrons go to the more electronegative atom. And we'll take a look at that. We saw that our product here, I'm going to draw it like this because that might be a little bit easier. If we break all our bonds, I'm going to use the correct color this time. We have to break all CC bonds homolytically because they are equally electronegative. By doing that, we now have C, C, H, H. I'm going to just forget about our CH3 dots because who cares about them? They're the same as, we don't care. We're not looking at those right now. And then heterolytically breaking them, we end up with the following. I'm sorry, I guess I should draw it on the other side just so I'm consistent. We see we have a -2 on these carbons. And so we have gone from an oxidation number of -1 to an oxidation number of -2. Both of these carbons have been reduced. They have gone lower in oxidation numbers. This is reduction. All right, and the hydrogen would be the one that's being oxidized. So, all right, let's take a look at it with something with oxygen. We're going to see that if we take a carbonyl compound, we can also treat it with H2, and we'll end up with an alcohol, putting an H on both the carbon and the oxygen. If we want to think about this the easy way, we want to look at, are we adding CH bonds or removing CH bonds? From left to right, we are adding a CH bond. Therefore, this is reduction. Done. If you want to calculate oxidation state, we can do that. We have no carbons here, so everything will be split homolytically, heterolytically. So all these go to the oxygen, because that's more, and we've also removed a CO bond. So we look at it either way, right? So they go hand in hand. We've added a CH bond, we've removed a CO bond. Both of those indicate reduction. So oxygen is more electronegative than carbon, but carbon is more electronegative than hydrogen. So we see here we end up with carbon 4 electrons, that's 0 as its oxidation number. If we're going to break this heterolytically, we see that we have carbon now with 6 electrons, giving it a -2 oxidation number. And as Jackson has pointed out, in conjunction with me, I said we added a CH, he said we removed a CO. That is two things happening, which is why we have -2. If somehow we only had one thing happen, then it would just be a difference of 0, but or one or something. Uh, it's another way of looking at your oxidation numbers. It's why it's 0 to -2, not 0 to -1 or something. With the previous one, we went from -1 to -2 because all we did was add a CH bond. We didn't remove a CO bond from the last molecule. So that's why those numbers are a difference by 1. In this case, because we have two things happening, we are losing a CO bond and we're gaining a CH bond. That's two things. That's why we have a difference of 2 in our oxidation numbers. And again, this is reduction. We're going to see later when we talk about what alcohols can do, we can oxidize them. So we can reduce carbonyls to alcohols, and we'll see later that we can oxidize alcohols to carbonyls. All right, so either way you look at it, it's pretty. I think this chart is a bit more of a straightforward way to identify whether reduction or oxidation is happening in an organic molecule. I like this way, but if you want to look at oxidation numbers, that's just fine. That'll always get you the same correct answer. All right, so either of these would be examples of that. Okay, so the point of all this is that we can take a ketone and reduce it to a secondary alcohol. We're going to look at reagents for doing this reduction. because H2 is kind of a crappy one. You can do it, but it's harder. It's relatively easy to take an alkene and do the reduction on it. It's a little harder to do it with the oxygen. So it's not very common. You could use H2 and PT. You could, but it's a crappy way of doing it. So let's um, let's not let's not use that. We're going to see if we take an aldehyde and reduce it, we are going to end up with a primary alcohol. So we can do these reduction reactions, and they will give us different types of alcohols. So ketones will give us secondary alcohols, and aldehydes will give us primary alcohols when we reduce them, right? Because we're adding a CH bond, and so in each case. So let's look at some reducing agents. There are two very common ones. We're going to see that one of them will be sodium borohydride. This is one we saw before in our um, demercuration when we were adding alcohols to alkenes. We're going to see that just like before, this serves as a way to give a nucleophilic hydride. So remember H minus by itself, as in sodium hydride or potassium hydride, is not nucleophilic. It is a base. So remember just KH or NaH are bases, never nucleophiles. So if we want to add a hydride as a nucleophile, we need to help it out. And one way to do that is to use it in the form of sodium borohydride. How this looks is, let's take acetone. Take something nice and easy here. What actually happens is we're just going to end up having our hydride attack, pops open the carbonyl. So now we have our H there. We now just have an O minus, right? That oxygen had two lone pairs, now it has three. So we have our counterion sodium hanging around. And typically we're going to see that the second step, we're going to add some acid to this. We could use water, but generally it's more common to use acid. And we'll protonate to make the alcohol. So as we can see, we have broken the CO bond and we formed a new CH bond. One sec, I'm going to close the window because I think the gardener from nearby. Let's see. It didn't really take away the sound. Oh well. Um, so we're going to see here that that reduction has formed us a secondary alcohol from a ketone. And so if we're looking like how we might write this, you'd say NaBH4, and then you'd have some acid, an acid wash. That will give you your secondary alcohol. Of course, this works on aldehydes as well. If you use sodium borohydride, you can get, you can get your primary alcohol out. All right, so sodium borohydride is a very common reducing agent. It is the gentle form of H minus. We have a more aggressive one that we can use. So this is on aldehydes and ketones, right? We can reduce those. We see that with other ones, like in ester, if we do the same situation, nothing happens. With esters, they don't reduce with sodium borohydride. But we have a more aggressive agent, reducing agent that we can make an alcohol from this ester. In fact, we'll make two alcohols from this ester. But be, we'll look at that later. And that more aggressive one is, as we'll see, lithium aluminum hydride will give us, we'll need actually two equivalents, or we'll say excess. We can say excess as well. That'll end up giving us our primary alcohol. We will have added two hydrogens here. And each one of those coming from the lithium aluminum hydride. So we'll add two hydrogens there. And on the other side, we'll make the ester. We'll make here. I'll make that a methyl ester. We'll also make methanol out from the other half. We'll take a look at what this looks like. We're going to see mechanism-wise, it looks essentially the same, except instead of boron, we have boron's friend, aluminum, one step below it on the periodic table. Comes in, opens this up, and now what's going to happen mechanistically, we have that O minus, we have our new purple H, which I will draw in purple, and then we have this. And so instead of stopping here, we're actually going to kick out that methoxide. We're going to see that reforming a carbonyl is a pretty strong driving force. And this is a reaction we're going to focus on a lot more next semester, but I'm still going to show the mechanism now so you see why we need two equivalents. So this will come down and it'll kick out our methoxide. So that's gonna be kicked out of our thing here. And so we will have now an aldehyde. And then of course now we're gonna have another lithium aluminum hydride molecule come along. And it's going to go ahead and pop that open. I'm sorry, I should be drawing these in purple. So now we've added two hydrides to our molecule. And then we just have our acid to protonate at the end. And we'll protonate our methoxide as well. So we use two equivalents there because the first one will open it up and then kick out the methoxide, or whatever your ester happens to be. And then you're going to have it happen again. And so it happens twice onto an ester. This will also work with Where's the? Oh my gosh! Come here. Okay. All right, Miss Jersey, you're gonna stay here. I don't know if y'all can hear Bailey barking in the background. Let's see. Oh, you can. Yeah, it's definitely. Oh well. Sorry. So with this, the lithium aluminum hydride will also work on carboxylic acids. So it'll do the same thing. If you have a carboxylic acid and treat it with lithium aluminum hydride, and then do your, and I'm just going to say excess to indicate that we have at least two equivalents in there. And then we're going to end up with our alcohol out. All right, and it will be a primary alcohol like before. It is funny watching the like. Yeah, I guess so. She heard something outside, either like the neighbor's gardener or whatever, and now she's gone nuts. And then she started Jersey barking, and then the whole thing starts and goes off. Bailey, come on. Let's see if she'll come back. So you can do this with carboxylic acids as well. If you try and do a carboxylic with sodium borohydride, no reaction. So you need the stronger reducing agent to get the carboxylic acid or the ester to react. All right, and so we're going to see that lithium aluminum hydride is a stronger reducing agent than sodium borohydride is. Sodium borohydride is the more gentle version. So, in the interest of paper chemistry, which is what we're doing, we write everything out, and yet it all works out great. In theory, yes, we don't really care about using one or the other if both will work. However, it's still a good practice to use the weaker one if possible. If sodium borohydride would work, you should use it rather than just using lithium aluminum hydride every single time. Because lithium aluminum hydride is more dangerous. It's a stronger reducing agent. It's more likely to explode. There are real life considerations to take into account here. So if you can use sodium borohydride to get your reaction to reduce, you should. If you have to use lithium aluminum hydride, then you'll use it. So I'm going to write that so that we have that on record here. Use that preferentially if it will work. So if y'all got an aldehyde, I don't want to see you using lithium aluminum hydride on it to reduce it. You're going to want to use the sodium borohydride. Haley, come here. I want to say hi to everyone. This is she's a new one. So she's 9 years old. As you can see, another Chihuahua. Um, she is the one who was doing all that barking earlier. Isn't that right? Are you a naughty one? No, you're a sweetie. So that's Bailey. So she's the smallest one now. So she's about 5 pounds. So just a small little thing. So, all right, go on, Bailey. So, point is here, we have two different reducing agents available to us. Sodium borohydride is the preferred one because it's less dangerous, because it's weaker. Always use the weaker thing if it'll work. Just like, if you're using a base and you can use sodium hydroxide, that's great. Sodium hydroxide is not very dangerous. If you're throwing sodium hydride at everything, though, like that thing will blow up in air. So, you're adding a lot more work in the experimental part of things if you use sodium hydride instead of sodium hydroxide. Same thing here with lithium aluminum hydride versus sodium borohydride. Use the weaker one because it's safer, less likely to explode on you. And it may not be written here, but sometimes these things, certain reagents need to be done in an oxygen-free environment. So you're using a glove box, or you're using dry solvents and all these things. You're taking extra precautions that you may not need to take if you use something less reactive. So that's the idea. So the less reactive stuff is better if it'll work. Okay, so those are our reducing agents. So that's our new ways of making alcohols. So do we have any questions on those before we talk about some reactions of another way? So these have hydride as a nucleophile. And what they will do is they will increase CH and decrease CO bonds. So you'll typically see an oxidation change of 2 because you're increasing CH bonds and you're decreasing CO bonds. We're going to see we have other ways of reducing carbonyls into alcohols using non-hydride things. And we're going to see that these will have different oxidation number changes. I'm going to introduce to you now something that you're going to find very helpful synthetically speaking. Although, first we're going to look at, yeah, we'll do it. Okay. I will introduce you to the Grignard reagent. This is a carbanion nucleophile. And it's going to be stabilized um, by magnesium bromide plus. We're going to see that if you take as some sort of alkyl halide, or in this case it's a bromobenzene, whatever it may be, if you add magnesium to this, what actually happens is your magnesium will insert itself in between the bromine and the carbon. And so what really happens is you end up having magnesium sandwich itself in between the carbon and the halogen. This works with chlorine too. You can have chlorine, although bromine is typically used. You can use chlorine. You end up forming this ionic complex. You have the magnesium 2 plus, a bromide, single bromide, and then you have your carbon negative, and it's stabilized by this. So this is often just described as a C minus nucleophile, and you might just see this as something like, this would be one way to write that. You could also have something like this. These are Grignard reagents. You can make them out of any alkyl halide, even if it's sp2, like the benzene one is sp2. Ethyl magnesium chloride is an sp3 hybridized one. Really, that's purple. Really, what this is it's ionic, essentially, although we may draw it as a covalent species. Typically, by the way, you do these in ether. That's your most common solvent. They must be done anhydrously. We'll see why. But they must be done anhydrously. No water can be around. And this is an example of an air-free reaction. If you have water around at all, your water will gobble up your Grignard reagent, because these are very strong bases as well. However, they are more likely to be nucleophiles unless you have acidic hydrogens around. The point is, though, we can use these as nucleophiles, and we can have them attached 2 to something. So if we take our ketone and we add our Grignard reagent, we're going to pop this open. That's now stabilized by the MIGBR. And if you just do an acid wash after, you have your benzene, and now you've got an alcohol at the end. So you can use these as carbon nucleophiles. They will open up your carbonyl, and you'll be able to make it into an alcohol with your acid wash later, and that'll get rid of your MIGBR. So, put an arrow there. Notice here, all we've done is removed one CO bond. So this is still a reduction reaction. We're still reducing this to an alcohol. Although this time, instead of putting a hydrogen on there, we're putting a carbon-containing group. So we've put a phenyl group on there. So it's a great way to make tertiary alcohols. A ketone and a Grignard reagent will make a tertiary alcohol. And you'd expect an oxidation change of just 1. We're not adding any CH bonds, but we are removing a CO bond. So we are still reducing this. With an aldehyde, you'll end up with a secondary carbon. Let's say we use ethyl miccal, because why not? First step, our Grignard with the ether, diethyl ether as the solvent. And we go ahead and have our reaction happen. We're going to end up putting an ethyl group on this, and we still have our H from the aldehyde. It's still there. So we see here we end up with a secondary alcohol. So if we want a tertiary alcohol, we could make it from an E1 reaction, or SN1 reaction. We could make it from an alkene as well. And now we can make it from a carbonyl by using a carbon nucleophile, from a ketone specifically. Although we'll see with esters what's going to happen with them. If we want a secondary alcohol, we can get that from a Grignard and an aldehyde put together. All right, so really, again, all that's happening here is we have our Grignard reagent acting as a nucleophile. It attacks our carbonyl, opens it up, and then we will just protonate it. We're going to see, however, with esters, we're going to have a similar thing happen. With esters, we need 2 equivalents of our Grignard reagent. If we do this, and let's say this time we're going to use cyclopentyl MIGBR, because why not? And our diethyl ether, and then third step acid wash. We're going to end up putting 2 equivalents on there. So the first one, and these are carbon nucleophiles. Remember, carbon is never a leaving group until next semester. So carbon is never a leaving group. So we end up with this thing popped open. We now have our cyclopentane on there. It's going to close down because that's a strong driving force because we have a leaving group. The methoxide is a leaving group here. It's not a good leaving group for substitution or elimination by any means, but for this carbonyl closing down, it is a good enough leaving group. And so now we have a ketone, and now again a second one of these lovely cyclopentide ions will come in, and we'll have the second attack happen. And we now have two cyclopentanes on there, and then we just protonate it. I'm going to just erase it because why not? That's all right. So we end up putting now two of those on, and we get rid of our ester part. So we will end up reducing this one twice. All right, so Grignard reagents, and again with now let's take a look at another one in a sec. So any questions on this one with the adding it to an ester? So you need to put an excess of your Grignard reagent because it's going to need to react twice. If you just put one equivalent, you're going to end up with a mess of products. You're going to have some that are singly attacked, some that are, you're going to end up with a ketone there. You'll have the tertiary alcohol, and you'll have your original ester left over. So you'll end up with three different things if you just use one equivalent. So that's always a bad idea. So just go ahead and push it all the way to the end and completely react it. Cool. If we try and do this with the carboxylic acid, this thing is just going to be like, ha, I'm done. Let's consider pKa's, and we'll see which side of the equilibrium this thing lies on. pKa of a carboxylic acid, 5. pKa of an alkane, 50. So this reaction is going to go favor the products by 10 to the 45th power. No chance in hell you're going to have the left side of this at all. This thing will explosively deprotonate your carboxylic acid. Explosively. If given the opportunity, a Grignard reagent will be a very strong base. So if you have anything even remotely acidic around, it's not going to happen. So even just very weakly acidic protons cannot be present if you have a Grignard. So if you try and do something like this, I don't know, let's use the isopropyl one. If you try and do this again, all you're going to get is that. That's all you're going to get. You're going to get propane. Boring. Not a good thing. So the point is here, no acidic protons can be present if you want to do a Grignard reagent. Remember that alcohols have pKa's of about 15, and so we're going to see a pKa of 50 will greatly outpace that. So you can't have any OHs around whatsoever, whether it's a carboxylic acid or an alcohol. Typically for this, we're looking at any OH. Those are going to be acidic. Can't have anything acidic with these, at least so far. So no OHs can be around. And so if you do want to get this reaction to happen, we have ways of protecting your alcohol. And so if we need to use a Grignard reagent, in the presence of an alcohol, we need to hide it. And we're going to introduce now the idea of protecting groups. So sometimes, and again, this is probably one of our first cases of it, but you sometimes need to do reactions that are sensitive to other functional groups. You cannot do a Grignard in the presence of any acidic protons. And so you need to get rid of those. And you can get rid of those by protecting your alcohols. And one very common way, there's quite a few protecting groups. There's tons of research going into protecting groups. But the trimethylsilyl ether is probably the most common. And so we can protect them, say, by doing, watch this. That's what I'll say. We're going to see that this thing, I'm not going to drop methyls. This is TMSCl, trimethylsilane chloride. It will act as a protecting group for us because if this encounters an alcohol, the alcohol is going to attack it. We're going to have a nucleophile attack an electrophile, kicks out a leaving group. You might be thinking, well, that's an SN2 reaction. SN2 reactions are not going to happen on tertiary centers. Silicon is much bigger than carbon is, so we're okay. With carbon, those methyl groups would block us from attacking, but silicon is much bigger than carbon is. So I mean, no, I'm not going to say that. No, I won't. Okay, so silicon much bigger, so it's able to be attacked. Those methyl groups are not in the way. It's big enough to be attacked in an SN2 style. And so you end up now having you have well, I guess we need to put in a base in here somewhere. Let's use how about triethylamine? Although actually pyridine is probably more common. Let's use pyridine. We'll use pyridine instead. Pyridine will deprotonate this thing, and pyridine will also grab up our chlorine, so that's very useful. So we will lose our pyridine minus. I'm sorry, it's got the proton on its H. It's plus. We have Cl minus. Remember, Cl minus is a nucleophile, right? So having pyridine in there gobbles up your chloride, so it makes it no longer available. Because otherwise, your chlorine could go and attack things and do all sorts of weird nucleophilic stuff. So we don't have an alcohol anymore, which means we can do our Grignard now that we've done this. I'm going to just make the note here that the pyridine, let's draw pyridine out. Pyridine grabs the chlorine and precipitates out. So it is no longer part of our reaction. That helps drive this forward, and it also removes Cl- from the equation, so it can no longer mess with our reaction. We don't want extra nucleophiles in here because we want our carbon nucleophiles. So why would we want extra nucleophiles around? So getting rid of that chloride with the pyridine is very helpful. Oh, I know why I put that there. That was the subtraction side. So we lose our pyridinium chloride. Great. Now we can say we'll have our reagent come in, can do its thing, and then we can do our acid wash, and we now have a primary alcohol that we wanted. And then to remove the TMS, very often you use T-bath. T-bath I'll show you in a second, and that'll deprotect it. So now that removes the TMS. T-bath is tetrabutyl ammonium fluoride. It's a fluoride source. Fluoride will grab our, it'll attack our silicon and kick out the oxygen, and then you'll just need an acid wash as well. So let's take a look at the whole thing. The T-bath removes, its job is to remove the TMS. So if we needed to get this to undergo a Grignard of some sort, I totally forgot to even include this in the product. Shame on me. There we go. Or let's just remove that H. Oh gosh. I forgot the whole point of doing this reaction was to put that carbon bit on there. So because we cannot do a Grignard in the presence of an alcohol, we had to protect it. We protect it with TMS chloride, trimethyl chloride. The silicon is big enough for the SN2 to happen, so we end up with this protonated OTMS. Pyridine can take off our hydrogen and then get the chloride out of the situation. We now have our protected alcohol, so we can go ahead and do our Grignard reaction. Wash that off. We end up with our alcohol, and then we can deprotect with tetrabutyl ammonium fluoride, T-bath. So F minus, typically from T-bath, is the way to remove this. And then we just do a final acid wash at the end to protonate things. So how that would look, if we were to say it, would say first step, TMS, Cl, and pyridine. You then do your Grignard. Third thing, you can actually leave your Grignard as you don't need to do the acid wash right away because we're going to do an acid wash with this step. And in that case, you end up with the alcohol here. You've got your alcohol, and then, there's all the stereochemistry that I didn't include there. You'd have, here, You technically have both enantiomers, but the original one stays the way it was. Let's flip this to the side so we can see. So this would be the series of steps you would need to do to get this reaction to happen. You need to protect your alcohol with the TMS chloride. You need to then do your Grignard. Then you remove your protecting group, and then you can do your acid wash. You end up with two isomers, diastereomers, in fact. They are not enantiomers, they're diastereomers, because that left one is still going to be the wedge. That's not affected by all this stuff. So only the one on the dash, only the carbonyl one is affected. And because the other one is far enough away, you'll probably get a mixture of both, 50-50, I'd say. It may be slightly more in favor of the backside attack, but it doesn't really matter. We don't have a huge nucleophile, so. All right. Cool. Let's see. Um, let's do some. Let's do some problems here. Let's say I wanted to take and I wanted to get this molecule out. And of course, our here. Stereochemistry in here. Doesn't really change anything, but there we have it. Stereochemistry, yay. So, what set of reagents would we need to make this happen? Let's look at our product and think, how the heck did we get this? What's different about these two molecules? That's where we should focus our attention. We're looking at what's different. We have this is different than that. Here we have an ester, and here we have a tertiary alcohol. And we also have two new ethyl groups. Hold on, I'm going to sneeze. So we know that a Grignard reagent, here we go, a Grignard reagent will add twice to an ester. Pentane, if we did a pentane, Kevin, we would have, interestingly, we would have this. We would have if we use the pentane Grignard reagent. Do you see why? Because the bond, this carbon here, this carbon is our carbonyl carbon. So we're not adding that carbon on. We're only adding two ethyl groups. 1, 2, 3, 4. Those are our new carbons. If we were to add pentane, a 3-pentane Grignard reagent, those would add 5 carbons twice. I mean, don't worry about my bad. This is part of the process, right? Is looking at these molecules and seeing, okay, what the heck is different there? And so it's sometimes hard to see which carbon is present in the product that's not present in the reactant. So with this, we see that we added two ethyl groups, and we started with an ester. So we think, how do we end up adding two carbon units to an ester? Well, we know that Grignards add twice to esters. And so probably somewhere in here, we have at least two equivalents of an ethyl Grignard reagent, because that would turn our ester into this tertiary alcohol with two ethyl groups. Do we see why that is? We've added two groups that each have two carbons to an ester. And think the ways to do that, the only way we know right now is to do a Grignard reaction. And of course, we know we're going to need all those acid washes and all that as well. So because we know Grignard just adds two equivalents of some carbon-containing unit, and it'll give us a tertiary alcohol. All right, so if we're thinking about the reagents, unfortunately, we can't just say done. Can't just do this because of that pesky alcohol up there on the cyclohexane. Remember, if you have an alcohol, that's going to mess with your Grignard. So can't do that. So our reagents, I'll have that there. We need to protect the alcohol first. So we need to put the TMSCl and then the pyridine. Then we can put our two equivalents of this. Then we need the TBAF and then our acid. We can combine those. That's fine. And then so that'll be our set of reagents necessary there. So protect. Then we can go ahead and do our Grignard reaction, and then deprotect, and then protonate everything, and that'll give us our product. All right, so I would we'll end 5 minutes early. That's okay. Start getting these going in your head. Start incorporating this information about the alcohols. In this case, we're still talking about how to make them, so we haven't really talked about how to do things with them quite yet, but this is a very important synthetic step. So far for us, we have two ways of adding carbons to molecules. We can, okay, I guess three ways. One way to do it is you can use the C triple bond C as a nucleophile, because that's acidic, right? The acetylide, remember this thing is a nucleophile. You can add two carbons, or however many are on this R group. You can add that to a molecule. That would work. Now we have another way. We can use Grignard to add things to carbonyls. So we can go ahead and attack carbonyls using this, and we can get them to turn. We can add carbons, and we can add as many carbons as we want, whatever Grignard reagent we choose to use. If I wanted to put 5 carbons on it, yes, I could use a pentyl Grignard reagent for sure. We also know one more way, which is add to Cn minus as a nucleophile, but that adds 1 carbon and a nitrogen, so not necessarily just carbons. So these are important steps because C-C bonds are hard to make. Carbon-carbon bonds are difficult to make, and they're very synthetically useful. We can build molecules now. So that's the whole point of this course, is we're going to learn how to build molecules bit by bit. All right, so that's it for today. I put the key up this morning for exam 3, so you can take a look. Just for the record, there the double bond in the second molecule, it could be different ways. You could put them in the same step. There's no reason you can't. TBAF and acid are compatible, so you can put them together, or you can put them in two steps. Doesn't really matter. With the second molecule, I have them as geminal protons. That's the more likely situation there. But I will be pretty lenient if you have it as a cis or transalkene. That would be probably okay. It would just be very slightly different. Okay. But the key is obviously y'all can go and see it, and you can see all those fun answers. Okay, so that's it. We'll see you guys next week. Enjoy your weekend, and we'll continue on next time. We'll finish off alcohols. Not much left to do, and then I don't remember if I'm supposed to talk about ethers in this class or if that's the next class. We'll see. But we'll go from there. So, okay, cool. Awesome. See you guys next time. Enjoy the rest of your day.